Physics is lying to us, not maliciously but through omission. We've built civilization on two flawless theories of reality that violently disagree, while the universe bombards us with signals that defy all known laws. Einstein's gravity and quantum mechanics are locked in a divorce so bitter, their clashes rip holes in spacetime itself. Black holes become mathematical scream zones. The Big Bang dissolves into paradox. Yet stranger still, reality keeps sending us encrypted memos. Unexplained radio bursts pulse from dead galaxies. Ball lightning phases through walls. Superconductors cheat thermodynamics. Even glass hides quantum mutiny in its frozen chaos. These aren't random glitches, they're breadcrumbs left where physics breaks. As we stand between the warring titans of theory and the universe's cryptic transmissions, one terrifying truth emerges. Our science isn't broken, it's being outsmarted by reality. The cosmos isn't just stranger than we imagine, it's whispering secrets we're not yet equipped to hear. And the ultimate revelation may force us to rewrite everything. Welcome to episode 2 of The Greatest Mysteries of the Universe, where we explore the cosmic divorce that could reshape everything we believe about existence itself. Let me tell you about the strangest relationship in science. Imagine two people who are both absolutely right about everything, except when they're in the same room together. That's Einstein's general relativity and quantum mechanics. General relativity is elegant, smooth, and predictable. It tells us that massive objects bend the fabric of space-time itself. Picture a bowling ball placed on a stretched rubber sheet. That's how the sun creates gravity, by warping space around it. Everything flows in beautiful, continuous curves. Time slows down near massive objects. Space itself can stretch and compress. It's geometry made real, and it's never been wrong. Quantum mechanics is chaotic, probabilistic, and fundamentally weird. It says that at the smallest scales, particles don't have definite positions or velocities until you measure them. Reality exists in multiple states simultaneously. The very act of observation changes what you're observing. These theories describe the same universe, yet they're speaking completely different languages. Relativity treats gravity as smooth, continuous curves in space-time. Quantum mechanics treats every other force, electromagnetism, the strong nuclear force, the weak nuclear force, as exchanges of discrete particles called bosons. Photons carry electromagnetic force. W and Z bosons carry the weak force. Gluons carry a strong force. But gravity, general relativity insists there are no gravitons, no particles of gravity, just curved space-time. The real catastrophe happens when you try to bring them together. Imagine calculating what happens inside a black hole, where gravity becomes incredibly strong and quantum effects become impossible to ignore. Mathematics doesn't just fail, it explodes. You get infinite energies, infinite curvatures, infinities upon infinities. In physics, infinity isn't a number, it's nature's way of saying you're asking the wrong question. This isn't just academic navel-gazing. Every time you use GPS, your phone has to account for both quantum effects in its electronics and relativistic time dilation from satellites moving at high speeds. We've built a technological civilization on two theories that fundamentally contradict each other. It's like constructing a skyscraper where the blueprints for the foundation and the blueprints for the upper floors were drawn by architects who refused to speak to each other. But here's what keeps physicists awake at night. What if the problem isn't that we haven't found the right way to marry these theories? What if the real issue is that we're missing something so fundamental, so obvious, that future scientists will wonder how we could have been so blind? There are places in the universe where our physics simply stops working. Not because our instruments aren't good enough or because we haven't done the math correctly, but because reality itself seems to break down. These places are called singularities, and they represent the ultimate failure of our understanding. Let's journey to the most extreme place we know, the center of a black hole. As you fall past the event horizon, that point of no return, general relativity describes your experience perfectly. Time slows relative to the outside universe. Space becomes increasingly curved. You experience spaghettification as tidal forces stretch you vertically and compress you horizontally. But then you reach the center, and both of our great theories have a complete nervous breakdown. According to general relativity, at the very center of a black hole lies a point of infinite density and infinite curvature, a mathematical monster called a singularity. All the matter that ever fell into the black hole is compressed into a point with zero volume but infinite mass. The curvature of space-time becomes infinite. The laws of physics simply give up and walk away. Quantum mechanics, meanwhile, starts screaming in protest. The uncertainty principle says you cannot confine anything to a point of zero size. Doing so would require infinite energy. Quantum field theory predicts that the vacuum near a singularity should be teeming with virtual particles popping in and out of existence. But general relativity's infinite curvature makes it impossible to define what vacuum even means. It's not just black holes. Wind the universe backward to the Big Bang, and you encounter the original singularity, a point where all matter, energy, space and time were supposedly compressed into mathematical nothingness. Before that moment, general relativity tells us there was no before. Time itself didn't exist. But quantum mechanics whispers a different story. Maybe the Big Bang wasn't the beginning of everything, but just the moment when a previous universe collapsed into a quantum-sized package suddenly expanded again. Maybe what we call the Big Bang was actually a big bounce, and our universe is just one breath in the eternal respiration of reality. We don't just have mathematical problems with singularities, we have a philosophical crisis. If the laws of physics break down at singularities, how can we trust them anywhere else? It's like discovering that your most reliable map becomes completely blank right at the destinations you most want to reach. Some physicists argue that singularities don't actually exist, that they're just artifacts of incomplete theories, like the horizon line that seems real until you walk toward it. Others believe singularities are real places where the normal rules of cause and effect simply stop applying, where new universes might be born, or where consciousness itself might play a fundamental role in shaping reality. The singularity problem isn't just about exotic objects like black holes. It's about the limits of human knowledge and whether there are some questions the universe simply won't allow us to answer. But what if there's a way to heal the broken marriage between our theories? What if the solution requires us to reimagine the very nature of reality itself? String theory. An idea so beautiful and so strange that it's captivated physicists for over 50 years. String theory proposes that everything, every particle, every force, every vibration of energy in the universe is made of incredibly tiny, one-dimensional strings. Think of it like this. If an atom were the size of the solar system, a string would be about the size of a tree. These strings vibrate at different frequencies, like guitar strings, and each vibration pattern corresponds to a different particle. An electron is one vibrational mode, a photon another, a quark yet another. Gravity itself emerges from a particular type of string vibration called a graviton. String theory is mathematically gorgeous. It naturally includes gravity as just another quantum force. It eliminates the infinities that plague other attempts to quantize gravity. It suggests that all the forces of nature, gravity, electromagnetism, and the nuclear forces, are really just different aspects of string vibrations unified at the deepest level. But here's the catch that has frustrated physicists for decades. String theory requires our universe to have 11 dimensions, not 4, 3 of space plus 1 of time, but 11. Where are the other 7 dimensions hiding? String theorists propose they're compactified, curled up so small that we can't perceive them, like how a wire looks one-dimensional from far away, but reveals its circular structure up close. Even after 50 years of the most sophisticated mathematics ever developed by human beings, string theory has made virtually no testable predictions. We can't build an experiment to detect strings directly. We can't verify the existence of extra dimensions. Critics argue that string theory isn't science at all, but mathematics masquerading as physics, beautiful, elegant, and possibly completely irrelevant to actual reality. Yet string theory keeps delivering surprising insights. It's helped mathematicians solve problems that had stumped them for decades. It's provided new ways to understand black holes and quantum entanglement. It's generated thousands of papers and launched the careers of brilliant physicists around the world. Even if it's wrong about the fundamental nature of reality, it's been incredibly right about the hidden connections between different areas of mathematics and physics. But string theory faces a deeper philosophical problem. It suggests our universe might be just one of 10 to the power of 500 possible universes, a number so large it makes the atoms in the observable universe look tiny by comparison. In this vast landscape of possible realities, every conceivable set of physical laws exists somewhere. Why do we live in a universe with our particular constants and forces? String theories answer pure chance. This drives many physicists to distraction. Science is supposed to explain why things are the way they are, not just catalogue infinite possibilities. If every possible universe exists, then asking why our universe has the properties it does becomes as meaningless as asking why you happen to be born in this century rather than some other. Meanwhile, the quest continues. String theorists keep pushing forward, developing new mathematical tools, exploring new landscapes of possibility. They're motivated by a dream that transcends any individual theory. The dream of a single, beautiful equation that describes everything. Every particle, every force, every moment from the Big Bang to the heat death of the universe. But what if the answer lies not in making reality more complex, but in revealing a hidden simplicity we've been missing all along? While string theorists weave mathematical symphonies in 11 dimensions, another group of physicists is taking a radically different approach. They're asking a simple question: what if space itself isn't continuous? What if reality at its most fundamental level is digital? This is loop quantum gravity, the rebel theory that suggests the universe is pixelated. Look at the screen you're looking at right now. From a distance, it displays smooth curves and continuous colors. But zoom in far enough, and you'll discover it's made of discrete pixels, tiny individual points of light that create the illusion of continuity. Loop quantum gravity proposes that space and time themselves have this same structure. According to this theory, if you could zoom into the Planck scale, about 10 to the power of minus 35 meters, smaller than atoms by a factor larger than atoms are smaller than humans, you'd discover that space is woven from tiny loops. These aren't loops of string vibrating in higher dimensions, but actual geometric loops that form the fabric of space-time itself. Think of it like chainmail. From far away, a knight's armor looks like a smooth, flexible surface. Up close, you see it's made of countless interconnected rings. Each ring is discrete, but together they form something that can bend, stretch, and move. In loop quantum gravity, space-time is the universe's chainmail, made of quantum loops so small we perceive them as continuous space. This has profound implications for black holes and the Big Bang. Remember those troublesome singularities where general relativity breaks down? In loop quantum gravity, they simply can't exist. You can't compress matter to infinite density because space itself is made of indivisible units. It's like trying to divide a pixel in half. At some point, you simply can't go smaller. This means that what we call the Big Bang wasn't the beginning of time, but a big bounce, a moment when a previously collapsed universe reached maximum compression and then rebounded into expansion. The universe might be eternal, cycling between expansion and contraction like a cosmic heartbeat. Each cycle could last trillions of years, with countless big bounces stretching into an infinite past and future. Black holes, too, become less mysterious. Instead of collapsing to a point of infinite density, matter reaches maximum compression at the Planck scale and then bounces back. Some loop quantum gravity theorists propose that black holes are cosmic wombs, places where collapsing matter reaches quantum limits and then explodes outward as new baby universes, each with slightly different physical constants. But loop quantum gravity faces its own challenges. While it elegantly solves the singularity problem, it struggles with other aspects of physics. It's difficult to recover Einstein's smooth spacetime from the pixelated quantum geometry. The theory makes few testable predictions, and some of its mathematical foundations remain controversial. More fundamentally, loop quantum gravity forces us to confront a disturbing possibility. What if time itself is an illusion? In this theory, the fundamental equations don't include time as we experience it. Instead, time emerges from the complex interactions of quantum loops, like how temperature emerges from the motion of molecules, even though individual molecules don't have temperature. This means the flow of time, the progression from past to future that seems so fundamental to existence, might be like a movie created from still frames. Each quantum state of the looped space-time is like a single photograph. String enough of them together and you get the illusion of motion, of change, of time itself. If loop quantum gravity is correct, then every moment you've ever experienced, your first day of school, your first car, reading these words right now, all exist equally in the quantum geometry of space-time. The past isn't gone, and the future isn't yet to come. They're all just different arrangements of quantum loops, equally real, equally present in the deepest structure of reality. But whether it's string theory or loop quantum gravity or some completely different approach, all attempts to marry quantum mechanics and relativity face the same ultimate question. What if the answer requires us to abandon everything we think we know about the nature of existence itself? Here's where our quest for quantum gravity leads us to the most mind-bending possibility of all. What if our entire universe, every star, planet and person, is just one bubble in an infinite ocean of realities? Both string theory and some interpretations of quantum mechanics point toward the same unsettling conclusion: the multiverse. Not parallel dimensions or alternate timelines, but a vast, perhaps infinite collection of actual universes, each as real as our own, each with its own laws of physics, its own history, its own version of you reading these words. In string theory, the multiverse emerges from that landscape of 10 to the power of 500 possible vacuum states we mentioned earlier. Each represents a different way to configure the extra dimensions, leading to different physical constants, different particles, different forces. Our universe exists in one particular valley of this landscape, but countless others exist in different valleys, with different properties. Some of these universes might be almost identical to ours. Perhaps there's one where you chose a different career, or where dinosaurs never went extinct. Others might be radically alien. Universes where electrons are heavier than protons, where gravity is stronger than electromagnetism, where time moves backward or doesn't exist at all. The quantum multiverse is even stranger. Every time a quantum measurement occurs, every time a particle's wave function collapses, every time you observe something at the atomic level, reality splits. One universe continues with the result you observed, while other universes branch off with all the other possible results. The radioactive atom that had a 50% chance of decaying doesn't just decay or not decay, it does both. In different universes, this means that every quantum event in history has spawned countless parallel realities. The universe splits every time a photon hits your retina, every time a neutrino passes through your body, every time any quantum system anywhere in the cosmos interacts with anything else. The branching is exponential, infinite, unstoppable. Right now, as you read these words, quantum events in your brain are creating countless parallel versions of yourself. In some, you're understanding these concepts perfectly. In others, you're confused. In still others, you put down this book years ago and became a professional juggler instead. All versions are equally real, equally conscious, equally convinced they're living in the real universe. But here's the devastating philosophical consequence. If the multiverse is real, then science as we know it becomes almost meaningless. Why does our universe have the particular constants it does? Pure random chance. Somewhere in the infinite multiverse, every possible value exists. Why did life evolve on Earth? Because in infinite realities, every possible outcome occurs somewhere. The fine-tuning problem that keeps physicists awake at night, why the universe seems perfectly calibrated for complexity and life, evaporates in the multiverse. Of course, we live in a universe fine-tuned for our existence. We couldn't observe ourselves in any other kind. It's like marveling at the incredible coincidence that you happen to be born on your own birthday. Some physicists embrace this conclusion. They argue that the multiverse is the natural consequence of our best theories, and we must follow the science wherever it leads, even if it makes us cosmically insignificant. Others recoil from it, arguing that any theory that makes all possible outcomes equally likely isn't really explaining anything at all. The multiverse also raises profound questions about ethics and meaning. If every possible choice you could make actually occurs in some parallel universe, does it matter what you choose in this one? If there are universes where Hitler was never born and others where he conquered the world, What does that say about moral responsibility? If every act of kindness is balanced by acts of cruelty in parallel realities, does goodness have any ultimate significance? But perhaps the most troubling aspect of the multiverse isn't philosophical, it's practical. If it's real, we can never prove it. By definition, we can only observe our own universe. The other realities remain forever beyond our reach, no matter how sophisticated our instruments become. We're trapped in our own cosmic bubble, able to theorize about infinite other realities, but never able to visit or verify them. This leaves us in a strange position. Our most sophisticated theories, the culmination of centuries of scientific progress, might be pointing us toward a conclusion that makes science itself impossible to validate. It's as if the universe is playing the ultimate practical joke on us, offering infinite answers to our questions while making it impossible to know which answer is correct. Yet the search continues, because maybe, just maybe, the real answer isn't about parallel universes or extra dimensions or quantum loops. Maybe it's about something we haven't even imagined yet, something so fundamental that it makes all our current theories look like cave paintings compared to Renaissance masterpieces. Let me tell you about the moment physics broke. It wasn't a dramatic explosion or a failed experiment. It was a mathematician sitting at a desk, working through equations and suddenly realizing that the numbers wouldn't stop growing. They kept getting bigger and bigger until they reached infinity, and then kept going. This is the crisis that haunts every attempt to unite quantum mechanics and gravity. When you try to calculate what should happen when these two theories meet, you don't get wrong answers. You get meaningless answers, infinite answers. And in physics, infinity isn't just a very large number, it's nature's way of telling you that you're fundamentally misunderstanding something about reality. The problem shows up everywhere. Try to calculate the energy of empty space using quantum field theory, and you get infinity. Try to figure out what happens to information when it falls into a black hole, and you get paradoxes that seem to violate the most basic principles of physics. Try to understand what happened in the first instant after the Big Bang, and your equations dissolve into mathematical chaos. Both quantum mechanics and general relativity are the most successful theories in the history of science when used separately. Quantum mechanics has been tested to an accuracy of 1 part in a trillion. General relativity has never failed a single experimental test. Yet when you bring them together, they produce results so nonsensical that they can't even be wrong. They're just meaningless. It's like having two perfectly reliable witnesses to a crime, each telling a completely coherent story. But when you try to combine their testimonies, you end up with a narrative where the victim died before he was born, and the murderer was in 17 places simultaneously. The infinity problem isn't just technical, it's telling us something profound about the limits of human knowledge. For 400 years, physics has been based on the idea that we can understand nature by breaking it down into smaller and smaller pieces. Study atoms to understand molecules, study particles to understand atoms, study quantum fields to understand particles. But what if this reductive approach has a fundamental flaw? What if reality isn't like a machine that you can understand by taking it apart, but like a hologram, where every piece contains information about the whole? What if the universe has an inherent unity that can't be captured by studying its components in isolation? Some physicists are beginning to suspect that the infinity problem is telling us we're asking the wrong questions entirely. Instead of trying to quantize gravity or geometrize quantum mechanics, maybe we need to find a completely different way of thinking about reality. Maybe space, time, matter, and energy aren't fundamental at all, but emergent properties of something deeper, something that can't be understood through traditional mathematical approaches. This is where physics meets philosophy in the most direct way possible. The infinity crisis is forcing us to confront the possibility that there are limits to what human beings can understand about the universe. Not practical limits. We might develop better instruments or more powerful computers, but fundamental limits imposed by the structure of reality itself. Maybe the reason we can't unite quantum mechanics and relativity isn't because we haven't been clever enough, but because the universe simply doesn't work the way we think it does. Maybe causality, locality, determinism, all the assumptions that underlie our approach to physics, are approximations that break down when pushed to their limits. If so, then the crisis of infinities isn't a problem to be solved, but a message to be decoded. The infinities might be telling us that reality is stranger, more interconnected, and more fundamentally mysterious than any equation could ever capture. They might be pointing us toward a completely new way of understanding existence itself. At 10:16 p.m. Eastern Time on 15th of August evening in 1977, the Big Ear radio telescope in Ohio was doing what it did every night, listening to the cosmic background hum of the universe. Radio telescopes are like giant ears pressed against the door of space, capturing whispers from distant stars, the death screams of black holes, and the gentle radiation left over from the Big Bang itself. But this night was different. The computer printout the next morning showed something that made astronomer Jerry Amon grab a red pen and scrawl "Wow" in the margin. The signal was impossibly strong, 30 times more powerful than the background noise. It lasted exactly 72 seconds, which is precisely how long it should take for Earth's rotation to sweep a stationary cosmic source across the telescope's field of view. The signal came from the direction of the constellation Sagittarius, broadcast on a frequency of 1420 megahertz, the natural radio frequency of hydrogen, the most abundant element in the universe. If you were an alien civilization trying to get someone's attention, this is exactly the frequency you'd choose. It's the cosmic equivalent of tapping someone on the shoulder. We've been listening for that signal ever since. 47 years of silence. The wow. Signal wasn't our first brush with cosmic mystery, and it wouldn't be our last. In recent years, we've discovered fast radio bursts, intense flashes of radio waves that last mere milliseconds, but release more energy in that brief moment than our sun produces in 3 days. They come from distant galaxies, billions of light years away, and we have no idea what causes them. Then there are gamma-ray bursts, explosions so violent they can outshine entire galaxies for seconds or minutes before fading away. When one goes off in our cosmic neighborhood, it could strip away Earth's ozone layer and trigger a mass extinction. The fact that we're here having this conversation suggests we've been cosmically lucky so far. These signals share a common thread. They're trying to tell us something about the universe that we're not yet wise enough to understand. Each burst, each pulse, each mysterious transmission is a piece of a puzzle we don't even know we're solving. But the cosmos isn't the only place where reality sends us encrypted messages. Imagine a world where electricity flows through wires with perfect efficiency. No energy lost, no heat generated, no waste. Trains levitate silently above magnetic tracks, reaching speeds that make today's bullet trains look like bicycles. Power lines stretch across continents without losing a single watt. Computers operate at impossible speeds, cooled by their own perfection. This isn't science fiction. It's the promise of superconductivity, and we're tantalizingly close to making it reality. In 1911, Dutch physicist Heike Kamerlingh-Onnes discovered something impossible while experimenting with mercury cooled to just a few degrees above absolute zero. The metal's electrical resistance didn't just decrease, it vanished completely. Electrons could flow through it forever, like water in a frictionless pipe that goes on for eternity. For decades, superconductivity remained a curiosity confined to the realm of extreme cold. Then, in 1986, everything changed. Scientists discovered materials that became superconducting at much higher temperatures. though higher is relative when you're still talking about temperatures that would instantly freeze your breath solid. We still don't fully understand how high-temperature superconductivity works. Classical superconductors make sense. Electrons pair up and glide through the material like synchronized dancers. But high-temperature superconductors seem to break every rule we thought we knew. The electrons shouldn't be able to pair up at such warm temperatures, yet somehow they do. The Holy Grail is room-temperature superconductivity, materials that work in the warmth of an ordinary day. In 2020, scientists claim to have achieved it, creating a material that was superconducting at 15 degrees Celsius. The catch? It only worked under pressures found at the center of the Earth. Not exactly practical for us, but imagine if we cracked the code. Magnetic resonance imaging machines wouldn't need expensive liquid helium cooling. We could build quantum computers that work on your desktop. Energy storage would become so efficient that renewable power could finally replace fossil fuels everywhere. The strangest part? We can make these materials work, but we can't predict which materials will work or exactly why they do. It's like having a key that opens certain doors, but not knowing what makes those doors special. We're engineers before we're scientists, builders before we're theorists. This pattern of useful mysteries that resist explanation appears everywhere in physics. Take something as mundane as the window you're probably looking through right now. You're surrounded by one of physics' deepest unsolved mysteries. It's in your windows, your smartphone screen, the lenses of your glasses. It's so common, so mundane that you've probably never given it a second thought. Glass? Nobody really knows what glass is. I don't mean we don't know how to make it. Humans have been crafting glass for over 4,000 years. We know the recipe: heat sand and other materials until they melt, then cool them quickly. What we don't understand is what happens during that cooling process, or why the result is so different from anything else in nature. Glass occupies a twilight zone between liquid and solid. It's not crystalline like ice or salt, where atoms arrange themselves in neat, predictable patterns. But it's not exactly liquid either. Despite the persistent myth that old window panes are thicker at the bottom because glass flows over time, that's just a quirk of how glass was made centuries ago. Glass is trapped. When you heat sand to its melting point and then cool it, the atoms want to arrange themselves into a crystal structure. But if you cool it quickly enough, they don't have time. They freeze mid-dance, locked in a random arrangement that shouldn't be stable but somehow is. This is called the glass transition, and it's one of the most studied yet least understood phenomena in physics. The atoms in glass are arranged like a liquid, but they're frozen in place like a solid. It exists in a state that theoretically shouldn't exist, too disordered to be a crystal, too rigid to be a liquid. The mystery deepens when you realize that glass transition isn't unique to traditional glass. Plastics undergo glass transition. So do certain metals when cooled rapidly enough. Even biological systems can enter glass-like states. It's how some organisms survive being frozen solid. What's happening at the molecular level during glass transition? We're not sure. Why do some materials form glass easily while others refuse to? We don't know. How do we predict which new materials will have useful glass-like properties? We're largely guessing. This ignorance has practical consequences. We make stronger glass by trial and error. We develop new optical materials through educated guesswork. We're still using techniques that wouldn't have surprised glassmakers from ancient Rome. Yet glass surrounds us, enables our technology, and shapes our modern world. It's a reminder that some of the most important things in life are also the most mysterious. Speaking of which, there's another everyday phenomenon that's equally baffling and far more dramatic. For centuries, people have reported seeing something that shouldn't exist: glowing spheres of light that float through the air, dance along power lines, and sometimes pass right through solid walls before disappearing without a trace. Science dismissed these accounts as hallucinations, optical illusions, or simple mistakes. Then we started making ball lightning in laboratories. Ball lightning is exactly what it sounds like, a sphere of plasma that behaves unlike anything in our physics textbooks. Witnesses describe balls of light ranging from marble size to basketball size, glowing in colors from white to blue to orange. They move slowly, sometimes following air currents, sometimes defying them entirely. They can last for seconds or minutes before either fading away or exploding with a loud bang. The reports are remarkably consistent across cultures and centuries. A glowing orb floats into a room during a thunderstorm, hovers for a moment as if surveying its surroundings, then either drifts out the way it came or vanishes into thin air. Sometimes it leaves behind the smell of sulfur or ozone. Sometimes it leaves scorch marks. Sometimes it leaves nothing but questions. What makes ball lightning so puzzling is that it seems to violate basic physics. Plasma, the fourth state of matter consisting of ionized gas, should disperse almost instantly at normal air pressure and temperature. There's no known mechanism that could keep a ball of plasma stable for more than a few milliseconds, let alone the minutes that witnesses report. Yet in the past few decades, scientists have managed to create ball lightning-like phenomena in laboratories. They've used microwaves, electrical discharges, and even silicon particles vaporized by electrical current. The results look remarkably similar to eyewitness accounts: glowing spheres that float, bounce, and eventually disappear. We can make ball lightning, but we still don't understand what it is or how it works. Each laboratory technique produces something that looks right, but might be based on completely different physics. It's like three different chefs creating dishes that taste identical using completely different recipes. Some theories suggest ball lightning is a plasma state stabilized by complex electromagnetic fields. Others propose it's not plasma at all, but something involving silicon nanoparticles or exotic forms of matter. A few radical ideas even suggest it might involve quantum effects or mini black holes, who, the truth is, we don't know. Ball lightning remains one of those phenomena that bridges the gap between the possible and the impossible, reminding us that nature still has tricks up her sleeve that we haven't even begun to understand. And speaking of nature's hidden tricks, there's one that affects every breath you take, every flight you've ever been on, and every prediction meteorologists make. Werner Heisenberg, the physicist who gave us the uncertainty principle, once said that when he met God, he would ask two questions. Why relativity? And why turbulence? He added that he was confident God would have an answer for the first question. Turbulence is everywhere. It's in the blood flowing through your arteries, the air rushing over an airplane wing, the cream swirling in your coffee, and the storms raging across Jupiter. It's one of the most common phenomena in the universe, yet it remains one of the least understood. Here's what makes turbulence so maddening. It looks chaotic, but it's not random. There are patterns hiding in the chaos, fractals within fractals, eddies within eddies, structures that repeat at different scales, like a cosmic Russian nesting doll. But these patterns are so complex, so sensitive to initial conditions, that predicting turbulent flow is nearly impossible. When air flows smoothly over a surface, we call it laminar flow, neat, orderly, predictable. But increase the speed or roughen the surface and something magical happens. The smooth flow breaks down into a writhing, twisting dance of eddies and vortices. What was once predictable becomes beautifully chaotic. The mathematics of turbulence are notoriously difficult. The equations that describe fluid flow, called the Navier-Stokes equations, are elegant and precise. But when turbulence kicks in, those same equations become virtually impossible to solve. It's one of the Clay Institute's Millennium Prize problems, worth $1 million to anyone who can prove that solutions to the equations exist and are unique. This isn't just academic hair-splitting. Our inability to fully understand turbulence has real-world consequences. Weather prediction beyond a few days remains fundamentally limited because the atmosphere is a turbulent system. Aircraft designers must rely on wind tunnel tests and computer simulations that approximate rather than truly calculate turbulent effects. Engineers building everything from pipelines to blood pumps must make educated guesses about how turbulent fluids will behave. But perhaps most remarkably, turbulence seems to be nature's way of mixing things up. Without turbulence, cream would never blend with coffee. Ocean currents wouldn't distribute heat around the planet. The interstellar medium wouldn't mix the heavy elements forged in dying stars. In a very real sense, turbulence is one of the fundamental processes that makes our universe interesting rather than static. Recent research has revealed that turbulence isn't completely chaotic. There are universal patterns, scaling laws that appear in turbulent flows everywhere, from laboratory experiments to distant galaxies. We're beginning to glimpse the hidden order within the apparent chaos, like finding the rules of a game we've been watching but not understanding. These patterns suggest something profound, that chaos and order aren't opposites, but dance partners in nature's greatest performance. And this dance leads us to perhaps the most intriguing possibility of all. As we've journeyed through these phenomena, mysterious signals from space, impossible materials, everyday mysteries, unexplained lights and chaotic flows, a pattern begins to emerge. These aren't just random curiosities. They're all symptoms of the same underlying truth. Reality is far stranger and more interconnected than we ever imagined. Consider the connections. The wow. Signal and fast radio bursts suggest the universe is alive with phenomena we don't understand, perhaps involving physics beyond our current knowledge. Superconductivity and the glass transition reveal that matter can exist in states that shouldn't be stable but somehow are. Ball lightning shows us that even simple plasma can behave in ways that violate our expectations. Turbulence demonstrates that chaos itself follows hidden rules. What if these aren't separate mysteries? What if they're all manifestations of deeper principles we haven't discovered yet? Think about it. Superconductors create perfect order from quantum chaos. Glass freezes disorder into stability. Ball lightning maintains coherence in conditions that should destroy it. Turbulence creates structure from seemingly random motion. The universe's mysterious signals might be trying to tell us about new forms of order hiding within apparent chaos. Each of these phenomena represents a boundary condition, a place where our current understanding breaks down and something new begins. They're like cracks in the facade of reality, revealing glimpses of the deeper structures underneath. The wow signal might not have been a message from aliens. It might have been the universe itself, trying to teach us about processes we don't even know exist yet. The patterns in turbulence might be showing us how information flows through complex systems. The stability of glass might be teaching us new ways that matter can organize itself. These mysteries share another crucial characteristic. They all involve the emergence of unexpected order from seemingly chaotic or impossible conditions. It's as if the universe has a hidden talent for creating stability, structure and meaning in places where they shouldn't exist. And this raises the most intriguing possibility of all. What if consciousness itself is just another example of impossible order emerging from chaos? What if the greatest mystery isn't out there in the cosmos, but right here in the 3 pounds of neural tissue between your ears? The signals from nowhere have taught us something profound about the nature of reality. Whether they're coming from distant galaxies or emerging from the materials in our own laboratories, they all point to the same truth. The universe is far more creative, far more mysterious, and far more interconnected than we ever dared imagine. But these mysterious signals and phenomena might not be random curiosities. They might be clues to a fundamental asymmetry that runs through the very fabric of reality, an asymmetry so profound that it explains why we exist at all. You see, the universe should be empty. The laws of physics tell us that matter and antimatter should have been created in equal amounts during the Big Bang, immediately annihilating each other and leaving behind nothing but pure energy. Yet here we are, made of matter that shouldn't exist, contemplating signals that shouldn't make sense, surrounded by phenomena that violate our expectations. What if all these impossibilities, the mysterious signals, the stable glass, the impossible superconductors, the coherent plasma balls, are all symptoms of the same cosmic rule-breaking that allowed us to exist in the first place? The universe, it seems, has a talent for the impossible. And nowhere is this more apparent than in the greatest impossibility of all, the fact that anything exists to ponder these mysteries. Why does anything exist? Why is there something rather than nothing? The answer to that question might explain every mystery we've encountered and reveal why the universe seems so determined to surprise us at every turn. In episode 3, we chase the ultimate asymmetry. We'll stare into the mirror universe, where antimatter reigns and time flows backward, and ask, could a shadow cosmos explain our existence? Then we confront the Goldilocks universe. Why is our reality just right for complexity when the multiverse offers infinite wrongness? The greatest deception isn't in the signals, it's in the silence of a universe that shouldn't exist at all.